class, which is to study the structure of Lie group and trying to reach the other half of the lecture, which is the Lie groups and the Lie algebras. And we claim that, well, Lie group is huge and has infinite members and dali, but we're able to just stare to the generators and do some trick of exponentiating that the more rigorous people might frown at my technique of doing it. But nevertheless, we're trying to study the structure of Lie group. So what do we mean by that? So let's say, suppose I have, so let's recall a Lie group is made of some group element, and which depends on, say, a tuplet, which this tuplet have n component, which n is the number we calculated again against as different group, has different number of real parameters. And this thing is just a notation for this bunch of things. So let's clarify the notation first. So if it has a subscript, it's one real parameter, and if it has a tilde, then it denotes this bunch. Okay, so then the next notation is, I'm going to use this notation says G alpha is nothing but a specific group element described by this tuplet, and alpha is really not an index. It's just a label. I want to label this guy to be different. This just means this is some other group element depend on some other tuplet. It's just a label so that I don't have to come up with 100 ways to write this small j in various different ways and try to keep track of all of them. So it's really not an index, so it doesn't run through anything. It just says this is a one group element to depend on some real parameters, and this is another group element. So I might as well label them differently. So I could just label them by smiling faces and not so happy face, and the one has the tongue out. It's the same idea. Oh, in my personal favorite, you know that I always want to teach you some Chinese. So this is a great time to introduce Chinese, because we have lots and lots of characters. We still have only, finite number of them, but we definitely has more power than the Greek people. So you could also label them by, this is Chinese in one, just like one line. And then you can label it 2 lines, so that's 2. And guess what? The 3 is 3 lines. So here is a task for your homework. Try to figure out how to write 1,000 in Chinese. It's not this. Yeah. Okay, but all these things, just try to emphasize, if you say an upper index, it just means it's a different group element. So what do I mean by structure of Lie group? Well, for any group, we have a binary operator says that I multiply 2 group member, I'll get some other group member. Right? But now we have the power of unitary matrices, as we're going to tell us that if we want to study physics and has operator and such, most of them will be unitary. At least we will only focus the unitary representation anyway. So there will be a unitary matrix representing this guy, which is a group member depending on some real parameters. And then similar for the second guy. And similar for the third guy. And then we can also just say this is a matrix that it depends on these real parameters, right? It's a matrix representation of this group member, which this group member depends on these real parameters. So this is a matrix, say M by M matrix, if it's an M-dimensional representation. It depends on all these real parameters we have in game. And the third guy, the thing on the right, we are in a determinist system. If I know these real parameters, which points to this particular group member, and if I know this real parameters pointing to this group member, then whatever come out of this must be some function that depends on the previous two sets of real parameters. So if I have two real sets of parameters, if I can find this function definitely exists because it's uniquely determined. I multiply two group members, I will for sure get that one, not anything else. And it has nothing to depend on except those two sets of real parameters. Yep.
What if you get outside of your chart by multiplying that?
What chart?
Like you're working in one chart of the Lie group, right? Or not?
Well, okay. I want to restrict myself to the part nearby the identity first. Yeah, I want to restrict myself to the identity, but you're pointing out I should already claim let's restrict ourselves to the part close to identity, so you never step far away. Okay, sure, we'll be technically correct and restrict ourselves to near identity. And that makes my life easier. So we'll choose the chart near identity and don't step too far away from it. Okay. Then, what do we mean by structure of Lie group? If I happen to know how to write down this function, we're done. If you give me any two real sets of a number, I know what's the function to map to a third real set of a number. Yeah, I know the entire structure of Lie group, how to do it. Well, this seems a mission impossible, but let's try to make some trivial and enlightening observation, as we like to do that. And how enlightening they are will soon reveal themselves. Okay, let's see. Since we're close to identity, so it's always good to choose the representation such that if we take all the real parameters to be 0, we get the identity. Then we can expand around them if they are small. Everything is nice. So that's a very nice thing to do, is when all the real parameters are 0, we get identity, which in representation, it's an identity matrix. Okay, the first observation I want to make is when both sets of real parameters are 0, what's the function would give me? Should be 0, because we know identity times identity equals identity, and it's a one-to-one map, so it maps back to 0. Trivial and enlightening. All right, now let's step one step further. Says, let's only leave one of them to be 0 and the other one to be arbitrary. Then what do we get?
The first.
The first one. Because this is due to the fun fact we learned says a group member times identity always gave the group member, which also works in matrix sense. And of course, we are always dealing with symmetric things. You would imagine if I take the other one to be 0, the other one to be arbitrary, we'll get it back. So step 0, I take everything to be 0. Step 1, I take one thing to be arbitrary. And now let's just take a leap of faith and make an educated guess what this function is. I don't know how to guess this. So we're sort of stuck. But as Thomas pointed out, we're close to identity. When they are close to identity, as we encounter again and again inside, that we will do expansion. small parameter expansion, hopefully we'll save our world and find this monster function. Or the expansion of this monster function. Okay, let's go ahead and expand things. So now I'll say this guy is a small parameter in all entries. Okay, a small parameter set. And I want to expand this guy. Near identity, so first entry would be identity. Then expand it. And then I'll just write the component now. Did I label them yet? No. I can use anything I want. Okay, small a runs through all the real parameters. And I'll call this exponent the expansion coefficient TA, which we remind ourselves it's a m by m matrices. For some silly reason that this always comes with an I, it's just a convention such that it's a convention that makes physics easier. Then you can expand with I, without I. So that you can consider this is like a Taylor expansion to linear order for a matrix, which we can do. If you want, you can just take the partial derivative of this guy with respect to this real parameter, and you'll get some coefficient, and you call them TA. Now this TAs has a name called generators, because they generate the group, or the representation of the group, which is the same thing for us. Okay, so we can always do that. And now we can already make some conclusion about these generators. They can't be quite arbitrary because that we have the unitary condition. So we know if we are studying a unitary matrix, it must follow this equation. So we can just plug our linear expansion in. And that's where it's very handy to choose a real parameter so we don't have to worry about that. And then the first term identity cancel. Those two multiply give you a second order, which we don't care. And in the middle one give us this guy. It should work for any small parameter, so we get rid of it. The I doesn't matter, we get rid of it. And then we move things around, we realize, these generators, if we happen to be happy to carry that I around, then this generators has a nice property of being Hermitian. So we have some observables, which we'll see this afternoon in the tutorial, that the generators are indeed very nice observables, such as momentum and angular momentum. Okay. So I guess this is how far I can get with linear expansion. Well, as math proceeds, if step one didn't achieve what we want, we'll continue. We expand everything to second order. Okay, I have to alert you, this is probably one of the longest calculations we're going to do together on board, which is shorter than some of the tutorials, sorry. But this is a very fruitful calculation. So we should really try to follow me and get this calculation done together. Okay? It's very fruitful, and we'll soon realize that. But it is long, because it's a second order expansion of this thing. Okay, so let's first expand this matrix in second order. Before we dig into the long calculation, will take us probably half an hour or 45 minutes. Depends on how many mistakes I make on the way. Is there any question up to now? Is it clear what our mission? Our mission is to find this function. And apparently we can't find it for arbitrary parameters. So we downgrade our goal. That goal is not reachable. And then we say, maybe we can find it when everything is small. And then in order to do that, we will expand to the second order, because the first order gave us something nice, which says the generator is summation. And hopefully, second order will tell us something about this function. All right. Well, I'm happy to write this down. This one is not hard. It will already expand to the second order. And the next order, it doesn't really matter. People point out it's a minus sign. Okay. But eventually you realize this part doesn't matter, but we'll expand it to second order. Okay? If you insist, I can carry a minus sign, but I have to change everything that I have in mind about this minus sign. But you can check, it doesn't matter. So it's really, there is one derivative, and now you do a second derivative, and call whatever left over this new thing. I don't know what it is. I know it's a bunch of m times m matrices, that's all I know. Well, I also know it's symmetric, because if it's anti-symmetric, it's 0 anyway. So that's how much I know about the second order expansion of this matrix, which is not much. But nevertheless, let's carry on. And now we are facing to expand this guy. All right. So for this function, for a, let's say, the eighth entry of this tuple that has n real parameters, I wanted to calculate what its second order expansion would be. So let's start with 0 order. So that will give me this. And then we'll start with linear expansion in the first guy, and then linear expansion in the second guy. And now I'll go with the second order expansion with using two different set of real parameters. And we also have the ones using the same. Cool. Okay, that should be all of it. I expand it all, and this is to second order. It's disgusting. Long. All right, so let's try to get rid of some terms by using our trivial and enlightening observation. All right, let's see. It says if you put them both to 0, they all disappear, and this guy should be 0. So this should never exist. Let's just get rid of it, right? So that's what this entry tells me. That if I take both arguments to be 0, I should just get 0. Shouldn't get something. Okay? Huh. All right, let's see what's the second trivial and enlightening observation tells us. It tells us if I have one of these guys, which means anything has a beta we throw away. We're left with only the guys include only alpha, which is these two terms. But then they say, if you set one entry is 0, you should just get back yourself. This, I didn't really do linear approximation. This is just the property of group multiplication says G times E equals G. So this really tells us we should have never got this term. This term is not going to give you this term. So this term gone. And further it tells us this guys should just be chronotic delta, which pick out the entry of A. Okay, good. So I'll save myself some time and claim by symmetry that this term will be gone. And then CBA should also just be the chronotic delta. Ha! So because we made some trivial and enlightening observation, it's truly enlightening, this whole thing disappears into 3 terms, and the 2 terms we even know. It says it's this guy plus this guy, and then there's this cross term that I can't get rid of. Well, it's good I don't. We'll say why. Okay, so there is some large number of coefficient there, but there are only 3 terms, and the first 2 terms are fixed. If you think about the U1, you can actually fix these 2 terms. It's really saying e to the I theta 1 times e to the I theta 2 give you e to the I theta 1 plus theta 2. So that's why we don't study abelian group. For abelian group, we know this function for sure. The function only has the 2 linear terms. And what is juicy about the non-abelian term is non-abelian group is that it has something hidden here. Okay, so now we have all the 2's. The only thing I need to do is expand this in second order. All right. So now we begin our really long calculation. Those are just preparation. Okay, let's do it. Well, not quite that one. That one with the infinitesimal parameters. So that will give that guy, so which is the expansion for the first set of parameter multiplied by the expansion. Okay, let me change some letters. For the second set of parameter, this is all it is on the left, really. Okay. So now let's do the second order expansion. It says the first entry is identity. It's probably going to cancel out. And then it has some linear terms. And then it has some quadratic terms. And then there is some cross-term quadratic terms. And then everything else is beyond second order. Right? So that's this, that, this, and that. All right. Let's look at the right-hand side. Right-hand side says we will take this thing as a parameter and stuck in there, right? That's what it says. is that u will expand u in terms of some small parameter, except the small parameter now is this expression. So this gives me 1 plus I. Yeah.
Should that be instead of B, C?
No. So this one's supposed to be C, but it's not ambiguous. I recall it.
Okay, you just relabel.
I'm just relabeling so that I try to use as fewer labels as possible.
Okay.
Yeah, so this one, you're right, this one was a C. But because in this line, it's ambiguous. So I have to label them differently. But now I have the freedom to relabel them. Okay. But let's stick that crazy thing here. That will be the first term. So as we take that function as our parameter, and we expand it to the first order for the unitary matrix. Now we just have to do it again to expand to the second order, which will give us this thing. Multiplied by itself with different label. Okay. So this is just another copy of this with every label changed so that it's not confusing. And this is what it is. All right. It's horrifying, isn't it? But at least, you know, we only care about to second order. So actually, a lot of things you don't care. Well, we do care about this first line. And there's nothing I can do to make it simpler. It's just 4 terms. It's this term. So you actually, I should have realized this is to first order, this is to first order, so I never really have to write these terms down. I'm just like giving myself own trouble. They're not going to give me a second order term. The second order term is purely coming from multiply these 2 linear terms together. Right? So that's making life somewhat easier. Okay, so let's write down what this guy gave us. So this gave me, and again, I'm trying to relabel things now that I can. So that's the first term. And then there is the one with both beta. And then there is the cross term. So there is this alpha, beta, LAB. And there is the other guy, which is beta, alpha, LAB. So that gives me 4 terms. It's not that terrible. And remember that LAB is symmetric. So then these 2 terms are actually the same. I can just name AB, name BA. And because they are this thing is symmetric, so these 2 terms are actually the same. OK. So now let's look at this together. I'll make use of all this cute chalk I have. So of course, we have 1 and 1 cancel. Well, if that didn't cancel, we never have to expand to second order in the first place. And then, to our delight, the linear term also cancel. which same argument. If the linear order has anything left, why do I take the trouble to expand to the second order? And to our more delight, this guy is canceled too. There's not much left from here. Okay, so we're left with one term here and two terms here, this guy and this guy, right? It's a lot of mass, but they all cancel. And some of them wouldn't even know they're canceling because we already done everything we can with the zeros and first order term, so they'd better cancel. So what we are left with, let me just rewrite it, is this guy. From the left, and then this guy from the right, and then the last term, which is this thing. All right, I'm just copying down whatever is left here over there, so we can do a little bit more manipulation. Okay, it's not that terrible. You expand both sides on the second order, and that's what we're left with. Okay, but the point of expanding in small parameters is eventually you want to claim this equation holds for any small parameters, then we can throw them away. That's the fun thing to do in life. And in our particular case, if I want to make these small parameters agree with the other small parameter, the thing I need to do is relabel things. So where I want B to be relabeled to C, C to be relabeled to B, and A relabeled by C. So then, oh, okay, that's not hard. I just want to, because they are all dummy index, I can call them whatever I want. So I do a rotation of index. Now I can happily throw them away, and we are left with this guy. Okay, right? The only thing I did is that it holds for all some small parameters, thus it must hold on its own. Okay, now what do we do? This is what we want. Remember, that's the only thing we have left from our monster function f. This we don't. So now we do something clever called rewriting the equation, but switch to index. And making use of the fact that this thing is symmetric. So I can just subtract. I'm going to use 2 subtract 1. And we get TA TB minus TB TA equals I dBAC minus dABC TC. And then this is just too long to write. So people rename this thing FABC. And the left side is a commutator. So we arrive at the commutator of 2 generator is given by some combination of another generator. And then we'll box this thing. And this is called the Lie algebra. Lie algebra is just some set come with a binary operator that is anti-commuting, because it's a commutator in our case, so it must be anti-commuting. All right, so this is what we get. To our delight, we never care about what's your second order expansion. It dropped out anyway. And this is what we want. And these things, these FABCs, have the beautiful name called structure constants. They're constants that we get from expanding that function and they describe the group structure. And now you ask, what do we do now? Well, of course, if you do the first order, second order, then we go onward to third order, right? And then I'm violating what I just said. I said I'm going to do this one long calculation today. So this is the fruit. This is the fruit that we're going to harvest. Because the mathematician did it. They actually go for, expand to nth order to that equation and see if we can find anything new. There's nothing new there. That's all it is. If you agree that the generator obey this relationship, then all the rest order would just work. So that's why they're called the structure constants. There's nothing else describing the group structure. That's it. So this is definitely something important, that we have structure constants. We should study these structure constants in depth and see what else it can give us. Well, first of all, the first thing is easy to observe. It is anti-symmetric in first two indices because it's a commutator. Okay. So before we discuss the property of the structure constant, are there any questions? No, just have to do this expansion on your own once. Oh, when you do the third time, then I feel I'm pretty confident about this calculation. Okay, so the next property is that these guys are actually real. So let's try to show that I claim this first property, they are anti-symmetric in the first index. And the second property, F, A, B, C's are real. Okay. To do that, we can take an adjoint of this thing. So I'm taking an adjoint of the entire relationship. If they are just numbers, they become the complex conjugate. If they're actually matrix, they have an adjoint. Okay? Now we use the fun fact that matrix AB, take the adjoint, they will switch. Okay, let me just write it out. So this is TA, TB, subtract TB, TA, taking the adjoint, which gave me TB adjoint, TA adjoint, minus TA adjoint, TB adjoint. But remember, they are generators. That's the first property we discover with the generators. They are actually Hermitian. So you can just throw away those things. And I realize after you take the adjoint, you get the commutator of TB and TA, which for sure will give us, according to this rule, it should give us IFBACTC, right? So this is just that line with A and B switched. But we can switch it back because the first two index is anti-symmetric. So we get that. And now, if we look at this guy and that guy, they should be equal because this is the adjoint of that. And that tells, well, the minus I are equal. T, the generator is adjoint of each other. of itself because it's Hermitian, and which tells us FABC star must equals to FABC. So now we know something more about the structure constant. It has the first two entry antisymmetric, and it is real. Okay. What else do we know about structure constant? Oh, rather, what do we know about the commutators? We know that the commutator anti-commute, because that's commutator. And what do you think if I commutator something else with the commutator? What do we get? So if I start out with this,
You can use the Jacobi.
right. There is a Jacobi identity says if I just cycle through the index, which is not the correct way. This should equal 0. And this is really, to prove this is really just open all the commutator. And you have like 2 terms from doing that, another 4 terms. So there are 12 terms, and then it's 6 paired up that they all equal to 0. There's nothing tricky. You just have to expand all the commutator. You don't even have to worry about if they're generators or not. Just use any matrix you want. Okay, very good. Then, because I have these cute relationships between generators, that is the Lie algebra, by using the Lie algebra extensively, 6 times, then you will arrive the commutator, the Jacobi identity for the structure constant. I'll just write it down instead of deriving it because it's really just a bunch of commutators and using that definition of the Lie algebra again and again. So, because the structure constants arise from commutator relationship, that we know that they will also satisfy this Jacobi identity. Actually, the inverse is also true. If we somehow find a set of numbers FABC that they satisfy this Jacobi condition, then we can build a Lie algebra out of it. So this is a very important property of the structure constant, is that they satisfy Jacobi identity. Okay, so now that's what I want to know for now, is that all the Lie groups can be studied at least nearby. The identity can be studied by some structure constant, which is the Lie algebra of the Lie group. And then these structure constants, they are antisymmetric in the first 2 indices. They're real. And they satisfy Jacobi identity. Okay? Any questions? So there's more things we should say about these structure constants. They're really constants. For example, in nowhere we cared about what's the dimension of M. you can use some different representation of your generators. You get the same structure constant. They are really describing the structure of your group. And of course, if you rescale your generator by some constant, then your structure constant will be off by some normalization constant. So that you have one set of structure constant and the other set, and the only difference is some normalization, then they describe the same Lie algebra. Also, as we'll note tomorrow, that you can also recombine your generators in some way. So you can do linear combination of your generators. Then your structure constant will change some way. It's like those similarity transformation. Yes. Okay, we're good with structure constants. And now we have this powerful tool. Says, well, okay, let me do this really sloppy thing. As a side says that how do I define this guy then? So how do I go back to the non-infinitesimal thing? I say, well, I'll just define this guy to be, I'll divide this guy up to be big n number of little pieces, and use the generator and exponential it, and I call this the exponential. That would be our group element. And then we take n equals infinity. And this is really using the fun factor of the natural number e. Okay, so we'll just define a group member that described by some finite parameters in this way. Except, when we multiply things that are matrix that don't commute, then it's fun to do. But there are mathematicians figure out how precisely this is going to work. And it gave rise some BCH formula, how to exponential matrices that don't commute. Okay, so from now on, we'll forget about there is Lie group and only focus on these Lie algebras. So what we're saying is, before, we say, we'll be happy if we can find all the representations of the Lie group. If you give me a group element and I assign it the matrix and preserve the multiplication, we'll be happy. Now our task is much simpler. We're down to n generators. And now I'll be happy as long as you just give me the representation of the generators. Then I'll just follow this recipe to get any group element you want. Because we just have mentioned, it completely describes the structure constant. If you know the Lie algebras representation, you in principle know the Lie group's representation. Okay? So from today onward, we only care about the Lie algebra. Well, tomorrow afternoon, in the tutorial, you will say some fun fact about some groups being homomorphic up to a factor of 2 and things like that. All right, so our task is to find all the representations for all the Lie algebras. Since there are infinite of them, I definitely need an infinite number of lectures to do it. But there is one good thing. There is one representation that exists for all the Lie groups. So give me a Lie group. Give me the structure. Basically, when I say give me a Lie group, I meant give me a Lie algebra. By that, I meant give me all the structure constant. And if you give me all the structure constant, I can at least build one representation for you. So this representation must be very powerful because it exists. Not the trivial one. The trivial one also exists for every Lie algebra. You just match everything to identity. But let's not do that. Well, no, you can't, you actually can't do that for the Lie algebra. You can do it for the group. Anyway, so let's talk about this. I'll write it here. So I'm trying representation, so for now, we have been using 2 letters trying to label things. One is a small n. N is the number of real parameters we needed. So it's also the number of the generators. It's also called the dimension of the Lie group. Because if it's an infinite group, we want to know how large it is. And one way is to label its dimension. And the other thing is some arbitrary dimension m, in which we try to find the matrix representation for the Lie algebra we study. And now, if there is a fun moment that when n equals m. So what if the matrix, we want to find a matrix representation, it happened to have the same dimension as the number of the real parameters. So such a matrix, which now is a n by n matrix, will certainly act on a n-dimensional vector space. And we can actually find such a vector space because we already have n independent things, like these generators. There are enough of them. They are independent. Otherwise, we don't need, because yesterday we tried hard to make sure that all the real parameters are independent. They are independent things. So we can certainly choose the generators themselves as the basis of the vector space and span it and build a vector space out of the generators. So in this picture, something crazy happened. The generators are something we want to represent them by matrix. But these matrices are acting vector space that is spanned by the generators. So generators, in this dimension, we have 2 rows. They are the matrix that are acting on a vector space. They are also the basis of the vector space. Okay. So if I want to represent my generator TA by a matrix TA and actually explicitly write out the matrix element, which I'll be using the same index, because now they are running through the same number, n. So before I have to use different index, because the index of the matrix tells us how big the matrix is, would run between 1 and m. M is whichever dimension you wish to find your representation in. But now, since I'm considering the representation in the same dimension, so all the ABC would run through between 1 and n. Okay. So now is the time that some people did the hard work, and I'll just say, I have a lucky guess for this number. Look, it has 3 indexes. It looks like my first structure constant. Why don't I just choose to be equal to my first structure constant to come with some coefficient? Well, it's a lucky guess. It has 3 indexes, and it might work. Well, this is the time to say if it works by looking at the Jacobi identity. And this identity would actually tell us this lucky choice of the adjoint representation, this guy, we represent. This literally tells I represent each of the generator by a matrix, and each entry of the matrix is the structure constant. Right? Okay, let's do this. So, yeah, this cute thing comes with minus i's everywhere. So I'm going to just multiply minus i's to everything. which certainly wouldn't change my Jacobi identity. Okay, so if I look at this, I can write this as my matrix with index BD. So that's what this one is, right? By definition, that's what happens. And then for the next one, I have TC has index DE, right? And for this one, I'm going to do a fun trick by switching this two index. So this guy, I'll write as minus FCBD. So this gives me minus TC BD, and this one gives me TA DE. And then there is this guy. Well, let's be cautious and not proceed yet, and try to say what do we expect. So this is really matrix multiplication. So this really tells me it's the matrix multiplication of TATC, and it's the BE entry. And that actually explained why do I want to switch the first two index so I can get a TCTA BE entry. Oh, this is nice. We almost get to the commutator there. So since it's a matrix with BE entry, that's what I'm looking for, which this guy has the chance, which again, I want to switch the first two index and pick up a minus sign on the way. And now, since everything is a matrix B entry, I can just drop that and rewrite it as TATC minus TCTA, which equals minus IFCAD TD. And I can use the fun trick again to switch. Lie algebra. So, because the structure constant always satisfies the Jacobi identity, and if I force the matrix representation of the generator to be given by the structure constant, then these matrices will form a representation of the Lie algebra. And this is known as the adjoint representation. And this exists for all the Lie algebra, because all the Lie algebra has some structure constant, and you can just build it this way. Neat, huh? All right. So for the next minutes, we're going to study some fun fact about the adjoint representation that requires some fun fact about compact Lie algebra. So it says that this is all cool, but if you have a compact Lie algebra, which says if the Lie group is coming from some manifold symmetry, then this manifold is bounded. So if, yes?
You mean Lie group, right? Because the Lie algebra
right.
is space.
You're totally right. Okay, so if the Lie algebra is coming from a compact Lie group, then Lie algebra has even further nice property, such as that FABC is actually completely antisymmetric. So in the notes, that you can check how this is proved. But so basically I use the fact that, remember that, that we have a vector space made up with these generators. And we can always define the inner product on this vector space. And one way of defining this is to take a trace of its adjoint representation. Yep.
Sorry, when you say compact Lie group, is that defined by FABC being completely antisymmetric, or what does it mean to be a compact? Sorry, what does it mean for it to be a compact?
For me, the compact Lie group really means, remember, Lie group has a bunch of real parameters. So if you write down real parameter theta goes from 0 to 2 pi, then it's a compact. If it goes to infinity, then it's not a compact. So I would say a compact Lie group is all the real parameters is confined in some finite interval. And Sarah has a better definition of compact Lie group.
Oh, it's compact as a manifold is like the Lie groups of manifold.
Right. Okay, so for when we have a compact Lie group, we can prove that, we can show that, we can define our inner product. We can always define our inner product this way. And if you check George's book, he has a cute way to show this can be written as orthogonal with some lambda. And the compactness will tell us all the lambda is positive, which means we can actually rescale all our generator by some like square root of lambda or something, such that they are actually orthonormal. So this is achievable in a compact, for the Lie algebra for the compact Lie group. And using this, we can actually show, well, just use that, we can show that FABC is completely antisymmetric. So you can see the derivation in the note. But now, if you take my word that this is achievable, then for this particular subset of Lie algebra that has this nice property, we can ask the following fun question. Says, if you tell me all the generators has a representation given by over there, so this is a matrix, which is the representation of the generator. But now we ask the fun question, what happens if it acts on the basis, which is itself. This is some generator, so this is really like EX. You make a huge column of all your generators, and then the generators could be 1, 0, 0, 0, 0, 0 in that particular vector space. And it's always interested to know what's the matrix acting on a basis. And to answer this question, we'll have to use the fact that it's possible to find the orthonormal base such that we can expand the identity. Yep.
Sorry, can you just clarify if capital T or little t is the generator?
So little t is the generator. It doesn't matter which dimension it is in. It can be anything. But we know there are n of them. And this n of them will expand the n-dimensional vector space. And the big T is very specific. It's a n by n matrix, and each of the entry is specifically given by the structure constant.
Thank you.
Okay. So now, if we are in orthonormal base, we can expand our identity matrix in this way. And that's what we'll do, is that in order to calculate this, I'll insert this identity But what is this? It is a matrix acting squeezed in the middle by two bases. So this is by definition the matrix element. So this is actually TA CB entry. But we know what is that entry. That entry is given by the structure constant, which is minus I F ACB. Okay, now we're going to use that it's completely antisymmetric to switch it into ABC, acting on TC. But they are just vectors, and they are certainly linear, so that I can pull the IFABC into the vector. So that's also a vector. This is a linear combination of the vector, and hence also a vector. But that is actually our commutator. That's our Lie algebra. Well, let's go. So what do we conclude? Is that if we act a generator as if it's an operator, this operator can, acting on the vector space formed by the n generators, and if we do so, it will produce the vector that is the commutator of the TA and TB. So this is a fun fact about adjoint representation, is that the important relationship to remember is this, is that I can go back and forth between using the commutator and the matrix acting on a vector. So now if we look it up, why it is completely antisymmetric, then we'll be all set. That's the part we skipped. Okay, so this concludes our discussion about the adjoint representation, which exists for all Lie algebras. And this afternoon, we're going to study Poincare group extensively, and we'll derive Poincare Lie algebra for at least once in my life. If you have done that, you can look at the optional problem. If you haven't, this afternoon will be the first time you do it. All right.